Welcome everyone. Thanks for joining this session. How Stripe achieve 5.5 nines of availability, joined by Stripe. Stripe supports a highly regulated financial industry around the world. It serves as a backbone of our economy, moving trillions of dollars globally every year. Because of this reason, its ability to function without interruption isn't just important, it's absolutely critical, ensuring that operations continue no matter the circumstances. My name is Balu Singh. I'm a Principal Solutions Architect at AWS. I worked closely with Stripe over the past 4+ years, helping them to build a resilient architecture running on AWS and build systems to achieve 5.5 nines of availability. Today, you're going to hear from two Stripe leaders, Abhishek Chatterjee, Head of Core Infrastructure, who will speak about the importance of why Stripe continually strives for high reliability, and David River, who will share the technical aspects of how they achieve high reliability. So why reliability is important? Why it matters? Let me give you an example. Reliable systems are not noticed until they fail. For instance, when you call fire department, you expect to be able to reach them. You expect them to be able to show up. That's not always the case. Almost 100 years ago, on the streets of London, a house fire erupted. Neighbors saw the blaze and called fire department. Unfortunately, the telephone system was down that hour. This meant that neighbor could not reach the fire department despite their repeated attempts. By the time fire department responded, it was little too late. This incident was preventable if only the telephone system had worked that day. So what did we learn from this incident? That reliability is not the property of best system on its best day or on its average day. Reliability is the property of worst system on its worst day when you need it the most, under load, under strain. Put more simply, under pressure, you're only as good as your weakest link. This incident gave birth to world's first emergency hotline in London, which in turn began the reliability campaign for the entire telecommunication stack. To this day, emergency response systems around the world target 99.9995% or 5.5 nines of availability. 5.5 nines means that in a month, system can tolerate only 13 seconds of unavailability. That is 13 seconds out of 2.6 million seconds in a month. That is 13 seconds, not a lot of room for error. It is common for consumer application to target 3.5 nines, which is roughly 22 minutes of unavailability in a month. But for Stripe, the bar needs to be higher because they enable the lifeline of business transactions. And they understand that resiliency isn't a one-time fix or a simple upgrade. It's a continuous journey, and for that, they proactively invested into it. And that brings us to why we are here today. Now, I would like to invite Abhishek Chatterjee to talk about the importance of why Stripe continually strives for high reliability.
Thanks, Balu. Hi, everybody. My name is Abhishek, and I'm the head of Stripe's Core Infrastructure organization. Core Infrastructure is a home for all of Stripe's Tier 0 mission-critical infrastructure systems that power our applications to run reliably and perform optimally at global scale. This includes our EC2-based compute instances, networking, database, our disaster recovery systems that run on multiple AWS regions, our cards and payments processing infrastructure, our edge, ingress, and DDoS stack. That's quite a large surface area that we manage. People often ask me, how do we build highly available systems? The real question is, why do we do it? Research has shown us that users will abandon a business if their payments are declined. And that number is a staggering 40%. You can just imagine how badly this impacts the business. At Stripe, our mission is to grow the GDP of the internet and deliver infrastructure that powers global commerce. So more than APIs, it is the value exchange that we drive in real time. Our users expect us to have a very high bar, which is why every transaction matters, every second matters, and your trust in us matters. We really, really care that our users have an exceptional experience using Stripe every day. The impact of unavailability goes beyond monetary loss. Big outages can put long-term reputational impact of organizations at stake. At Stripe, we have to process every transaction really, really fast. We have to prevent fraud. We have to make sure that the money ends up where it needs to be. And we need to make you look good doing it. Because after all, Stripe is integrated into your applications. When things go well, no one notices it. But when they go bad, it leaves a lasting impact with your users. And this is what it means to be available. We treat every transaction with the same level of seriousness as the emergency hotline systems that Balu was mentioning earlier. It's literally life and death for us. So, what is the secret sauce behind all of this? Well, technology is definitely at the forefront. But reliability is not just a metric, it is a mindset. And today, we are going to break down our talk into two parts. David, my colleague from Stripe, is going to come and explain about the technical aspects of reliability and availability. And I'm going to come back later and describe how we have built the culture of reliability at Stripe and how that culture enables us to be successful. David?
Thanks, Abhi. I'm David Reaver, a principal software engineer at Stripe. Stripe engineers deeply understand that failure is inevitable. However, that doesn't mean that your users have to know about it. I'm going to discuss technical strategies that Stripe uses to maintain our 5.5 nines of availability. And the goal of this part of the talk is for everyone to walk away with at least one thing you can bring to your systems and organizations to maintain high reliability. When something fails, it isn't enough to ask, why did this thing fail specifically this one time? You also have to ask, how can we reduce the blast radius of this kind of failure in the future? Put another way, we ask ourselves, if this system fails again for any other reason, how can we affect as few users as possible? It's good to think about how to reduce the blast radius of similar failures that don't necessarily share a root cause. For example, say a database shard is experiencing intermittent write failures. It's seeing a lot of writes, some of them are failing, not all of them. We of course ask, why is this happening? It could be a flaky disk on the primary node, there could be CPU contention, there could be a buggy query, whatever it is. Fixing the root cause of this failure is important, but we always go a step further. We assume that will always be some way that Murphy's Law is going to hit us. A database shard is always going to find a way to go down. So we think, how can we reduce the blast radius of that kind of failure? In this specific case, we might think very hard and come to the conclusion that we need to reduce the size of our largest shards because if any shard goes down, it will affect the fewest amount of users. However, there are actually ways to design blast radius reduction into your architecture at a fundamental level. Cell-based architectures are a common way to bake that into your systems. Stripe uses cell-based architectures in many of our systems. Cells are basically isolated copies of a system that independently serve traffic. So in this example, the cell router would accept a request, it would map that request to an individual cell, and once the request is in a cell, the cell handles the request end to end without talking to any other cells. This helps to isolate failure in a system. So for example, if cell 1 goes down, then only a third of your traffic about would go down. Now 1/3 is not great. Usually you have hundreds of cells, but I'm not gonna fit a slide with 1,000 cells on it. Cell-based architectures are neat, but there are costs. The biggest one is it's more technically complex. So if you're a startup and you're watching this talk and you think, that's great, I want to do what Stripe does, start with a monolith. Monoliths are way easier to reason about. Take monoliths as far as you can take them. Then as you start to think, as you start to understand your system and its properties, you can expand to a cell-based architecture in the future. Also, cell-based architectures usually require more hardware. You can't amortize headroom. So for example, in a monolith where all of your servers are talking to the same users, if one user has a spike once in a while, you can use some hardware from somewhere else to handle it. In cells, you have to make sure that each cell can handle traffic spikes by themselves. So on average, you'll use a little bit more hardware. Cells are not just about preventing random failures. At Stripe, they're also involved in change management. So we roll out internal software and architectural changes one cell at a time. So if we do something wrong and there's a bug, only one cell and only a subset of our users will experience it before we automatically roll back and don't touch all the other cells. One pro tip with cell-based architectures, you can introduce them incrementally. So it's a common misconception that cell-based architectures have the same cells throughout your whole system. So the misconception here would be Stripe has one cell router and each cell is a copy of Stripe. That's not the case. We use cell-based architectures independently in our storage subsystems, in our API service meshes, things like that. So don't think you have to do it for your whole architecture at once. When a system fails, oftentimes outright failure is one of the very best outcomes. For example, if a node is unplugged and there's no power, it's usually pretty easy for clients to detect that. They'll see failing health checks. After a few seconds, they can say that node's not healthy, I'm gonna go to other nodes. It's much harder to detect and remediate gray failures. And we define gray failures as partial or intermittent issues that are much more subtle to detect than outright failure. Some examples of gray failures. You can have high disk latency caused by a failing storage volume. You can have high network latency because some downstream router is dropping packets. You could have noisy neighbor issues, especially in modern architectures with Kubernetes. You could have a pod on the same node as another pod and it's sucking up all the CPU. In gray failure scenarios, failure can be very sporadic. It's not as clear cut. So it's harder for clients to detect that a node is unhealthy. For one, you can have health checks that are kind of flapping between healthy and unhealthy. So it's hard for a client to know, is this node healthy? Secondly, you could have passing health checks, and the gray failure manifests as very poor performance, which is very hard for a single client to detect. At Stripe, we use anomaly detection to automatically discover nodes that are misbehaving relative to their peers. A good metric to use for this is request latency. So for example, if we have a fleet of stateless API nodes, we'll send all of their request latency metrics to a central system. And if we detect that one node has much higher latency relative to its peers, we'll pull that node out of the service mesh. We'll keep the node around for investigation, but it will no longer serve traffic. We'll just assume there's something wrong. 2 pro tips for getting started with anomaly detection. 1, when you're starting out, assume that only one node at a time is going to experience gray failure. If you allow your brand new gray failure system to operate on wide swaths of your fleet, you might have a bad time. If there's an availability zone that's having elevated latency, you don't want your brand new system to take out a third of your fleet. That wouldn't be very good. Also, don't let nodes self-report anomaly detection. So don't think that you can go install an agent on all your nodes, like your brand new code to go detect anomaly detection. It'll fetch metrics and compare the nodes' latency to other nodes. You need to have an outside system do it. Nodes that are potentially failing are very untrustworthy. You can't trust what they say. So it's much more robust to have an outside system looking at metrics, deciding if nodes are unhealthy. This year, Stripe moved a huge chunk of our database storage systems to EBS. We did this to simplify our architecture and increase reliability by reducing the time it takes to rebuild a failed node. During the migration, we experienced some latency issues caused by some legacy systems that had very poor queries that would ruin the database's cache as they ran. Now, the vast majority of the time, we knew it wasn't a problem with EBS. We were within our IOPS limits, our throughput limits. We were seeing the advertised performance from the different volumes we were using. When this happened, we would try standard debugging tools. Of course, we'd look at the query. Why is it fetching so much data? We'd look at the Linux file system. What's happening with the cache? We'd look at the block layer. What's happening with latency? But almost always, we wanted to go a step further. And we wanted to see exactly what EBS saw. EBS has been an excellent partner for our business in this. When we faced this challenge, they worked closely with us to fully understand the issue. And as a result, they developed and deployed new features specifically designed to address these gaps. For example, they recently released CloudWatch metrics that will show you if you're hitting your IOPS limits or throughput limits. And also, they have a CloudWatch metrics to tell you if a volume is potentially failing. Also, as of last month, EBS now exposes detailed performance metrics through the EBS block device in the Linux kernel, so you can see very, very fine-grained details about what EBS sees. Now, with these new metrics and these new systems, we can very, very confidently and quickly diagnose if an EBS volume is being throttled or if it's unhealthy or if there's a problem somewhere else in our stack. So it saves us a lot of time and energy whenever we see query issues. So gray failures are nasty, anomaly detection is really cool, but are there other ways to protect against gray failures? Systems fail in similar ways. You don't want to relearn the same lessons you learned in some service in another service. You want to proactively figure out how to prevent or detect and remediate these gray failures. So one answer to this is at Stripe, we use chaos testing and fault injection. Chaos testing is a large subject, but in this context, I'm talking about simulating node failures and grade failures by purposely adding faults into the system and ensuring that your automated remediations work. Some examples of fault injections, you could purposely use IP tables to increase network latency by dropping packets, or you can just shut off networking on a node. You can run an infinite loop on a CPU to simulate CPU contention from a misbehaving pod on the same node. You could also introduce artificial disk latency or just drop some writes to simulate misbehaving disks. At Stripe, we have a chaos testing framework that runs around our systems and injects these faults so that we can ensure these systems automatically remediate themselves without human intervention. We encourage teams to turn these on for their service. Now, we don't go on day one of a brand new service and turn on all the faults and expect you to handle it. You'll just get paged and everyone will be sad. So over time, as your service gets more mature, you turn on more faults. And we let the system run in QA all the time. That's where you'll see the issues the most. But we can also turn it on in production in very controlled scenarios so that we can be very, very confident that production can handle these failures as well. Many systems have very spiky load, which means that they operate very far from peak traffic most of the time, and once in a while, they'll see a huge spike in traffic. Now, we all want to design systems with tons of headroom so you don't get paged in the middle of the night when a user has a lot of traffic. But there's a cost. For one, hardware is expensive to have this extra headroom. If you want 10x the available headroom, you might need 10x the hardware. Also, sometimes it's technically challenging to scale a system past a certain point. So you have to pay very expensive engineers to go figure out how to do that. And traffic spikes are not annoyances. Especially at Stripe, traffic spikes occur during the most important times for our users. They could be big sales, big events. They could be migrating some system from another system they need to dual write once in a while. For example, we just had Black Friday, Cyber Monday. It's the largest event of the year for many of Stripe's customers. In fact, 35,000 merchants that use Stripe had their highest revenue day ever last week. Also at Stripe, BFCM becomes our new normal baseline for the next year. So this isn't just a spike. This is our new normal going forward. Now, failures during these important events are extra painful and extra visible, so we absolutely cannot fail. And we can't use all-time high load as an excuse for failure, because if we do that, we're telling our users that when they have a good day, it's hard for us and we don't like it, which of course is not the case. So don't let your highest traffic days happen from user traffic. You have to load test your systems ahead of those all-time highs. At Stripe, we use massive synthetic traffic to punish our systems at many times the load of peak user traffic. These load tests enable to, first of all, uncover our weakest links. So when you do a load test, something eventually will fall over, and you have to find that specific subsystem, optimize it, and figure out how to make it better for next time. Also, load tests help you identify the resources of exhaustion before failure. So for example, you might have a system that's totally fine during the load test, maybe 50% CPU utilization, you start seeing some latency increases, you can note that down. And maybe at 80%, you start seeing errors. So even if the system survived the load test, the operators of that system know, okay, 50% CPU is something to watch out for, 80% is something to really watch out for. They might page, they might optimize, they can dig in further. Lastly, you see how well each component scales with load, so you kind of identify your next hotspots. Don't let them surprise you. Now, we constantly load test both individual subsystems, and we load test end-to-end flows for our API. We load test further and further. So we load test, find something to fall over, optimize it, repeat and repeat and repeat. So we're always staying way ahead of what user traffic will show. One pro tip is sometimes you can use load test to identify opportunities to make your systems more efficient at lower scale. So for example, you might have a system with a poorly performing database query. At low load, you don't really notice it. Maybe your latency is higher, but you're within your SLOs, you don't really care. During the load test, that query might knock your service over. So you see that, you optimize it. Then when the load test is done, you notice like, oh, our latency dropped by 30%. So it's a nice benefit of doing load tests. So the next topic is on continuous delivery. Stripe deploys tens of thousands of changes per day across thousands of services. The vast majority of these deploys are triggered via a git commit getting merged, and then there's no human in the loop after that. Continuous delivery is classically marketed as a way to reduce time to market, increase developer velocity, basically waste less developer time on manual, tedious deploys, which that's fantastic. That's a really good reason to adopt it, but I would argue that continuous delivery plays a larger role in reliability. For one, automated deploys are consistently repeatable and they remove the chance of human error. So for example, you have fewer self-inflicted incidents because someone pressed the wrong button on the deploy UI, or someone is reading a runbook with a bash command and they leave a space out and have an extra quote, and then you nuke a file system. That's not going to happen if a computer is doing these deploys. Second, more frequent deployments means fewer changes per deployment. So in the best case, for example, if you have a single git commit per deploy, if you see an issue during that deployment, you could be pretty sure that git commit caused it. You'll have the diff right in front of you. It's like being served the root cause of an issue on a silver platter. If you deploy once every month, you have a lot of changes to go through to figure out what happened. Lastly, one additional benefit of continuous deployment is that if change is constant, you minimize the cost of fleet-wide changes. So for example, you might need to do a security update across your fleet because some issue happened in the world. You might need to do a large migration in like a core library in a mono repo. If you have continuous delivery already implemented, you can make those changes, merge it, and then you can sleep soundly at night that it will get deployed. And if there's an issue, you'll detect it with your health checks for these deploys versus having to manually babysit thousands of services for your migration. When a request to an API fails, one obvious but often forgotten solution is to simply retry. For APIs that can handle retries, if you have a failed request and you retry and then you're successful, you'll have a little bit of extra latency, which is not the best thing, but a little bit of extra latency is better than failure for some of these APIs, especially for Stripe's payment APIs. Retries can be done at the client level, so users can write custom code to implement retries on themselves if they see a failure. You can also ship it in your SDKs, so like the AWS SDKs are a good example. You add a couple lines and you get great exponential backup retries. Stripe users are totally free to do this, but we highly prize how easy it is to integrate with the Stripe API. So we don't want to burden our users to have to do this to get the reliability benefits. We prefer to do retries on their behalf. We usually take a request from a user, we accept it as close to them as possible, and we send it to the correct geographic region for processing. And then we do retries in that region for them. So doing retries on behalf of users gives us a number of benefits. For one, the most obvious is from a user's point of view, they'll see less flakiness in the API. They'll see fewer errors. They might notice the extra latency once in a while if there's a problem, but they'll see fewer errors. Also, the retries happen inside our network. So a huge benefit of this is they'll see less overall latency from a retry. So for example, if a user in New York sends us a request, we'll take that request and maybe send it to Oregon for processing. If there's an issue in Oregon, we will retry in Oregon before sending the request back. The alternative, of course, is you go from New York to Oregon, fail, go back to New York, sorry, try again, succeed, hopefully, and you don't have to go back. But that's a lot of latency. Lastly, when we do retries on behalf of our users, we can use our internal knowledge of our architecture to do them more efficiently. For example, we could retry in Oregon on a different cell in the database cell-based architecture instead of retrying the same cell over and over. Or we could retry in Ohio instead, because maybe Oregon's having problems and we click a button and say, we need to get out of there. A few pro tips with retries. One, first, ensure that your API can handle retries. Don't just put a loop, oh, failed, gonna try again. You could have problems if your APIs are not idempotent. So design your APIs with idempotency in mind to make them able to handle retries. Second, beware implementing retries in too many layers of your stack. You should always prefer to retry at the furthest layer, closest to the user. So for example, if you do retries at your database layer, your backend API layer, your front-end layer, then one database issue can manifest as 10 retries here, 100 retries here, 1,000 retries here. That's request amplification. You don't want that to happen. So it's more robust, especially when you're starting out, to just retry at the very outer layer. Lastly, retries are a very useful tool to allow you to take very short bursts of downtime. In our case, in our database systems, sometimes we'll have a primary failover and we'll have a leader election. It lasts a few seconds, but you can't do writes during that time. So in our internal database SDK, we have retries configured so that users won't notice that. They'll see a little bit of extra latency, but they won't see a bunch of failing errors every time we have a failover. Sometimes our 5.5 nines of overall reliability isn't evenly distributed among our users. It could be that one of our cells is down in a subsystem, so a very small number of users are affected. We could have a bug on our end, like a feature flag gone wrong and some users opted into that feature flag are seeing errors. Saying that Stripe aims for 5.5 nines is excellent for marketing, and we meet that overall, but really users care about their view of our traffic. If the rest of Stripe is up but they're down, they don't really care. They care that their traffic is down. They don't care about the overall 5.5 nines. So Stripe has lots of systems in place to proactively alert users when they're having a particularly bad time. One cool thing we do, for example, is we don't solely rely on standard HTTP response codes to decide if a request is successful or not. So classically, if you don't know, if you have an HTTP response of 200, you say that's great. 500 is it's an error and it's our fault, and 400 is it's an error and it's your fault. That's too simple. We don't do that. There are lots of legitimate 400 responses that are kind of routine and expected. You'll see, you can't just page on them all the time. But we monitor for spikes in 400 responses. Because that could mean there's a bug, maybe in a user's code. It could mean there's a bug in our code. Again, maybe there's a feature flag gone wrong that we're trying to not authorize some of the requests, but they made no changes. So we monitor for this and we tell users. We also expand this anomaly detection for specific APIs, specific payment methods, and even to latency. Now, we often work with our users to improve their integrations. So we'll reach out and say, hey, we see something inefficient. You're making 10 API calls when there can only be one. This helps us. It's a huge win-win when we do that because their systems are more efficient. They'll see less latency. They'll see less cost. And it makes us more reliable because we'll have less load from that user, and then we have more hardware left for the rest of Stripe. Now I'd like to hand it off to Abhishek to go beyond technical bits and talk about how Stripe builds a culture of reliability.
Thank you, David. So as I was discussing earlier, reliability is not just a metric, it is a mindset. And today, I'm going to share 3 practices at Stripe that has allowed us to build a culture that values reliability. Our first practice is practice your worst day every day. At Stripe, we exhibit extreme curiosity about all our systems. We push them to their breaking point using various scenarios. We do this because we want to know how those systems fail. And once we know the limits for those systems and the failure modes, we instrument them in our design thinking so that we can iteratively make our systems even better and more reliable. We only use systems in production once we know their limits. Or in other words, we only run well-tested and vetted systems to serve our production traffic. A key to preventing failures and user impact is to accept the fact that failures are inevitable. So at Stripe, we design systems from the ground up that can tolerate such failures. We don't know how and when a system might fail. So hence, we focus on making resiliency a critical part of our systems using the techniques that David mentioned earlier. We combine technology with world-class observability so that we can detect any degradations or failures early enough before they start impacting our users. And we have invested in a lot of automation and self-healing in our systems so that they can detect degradations using, in various scenarios, and they can recover from them automatically without us having to do anything. Think about a circuit breaker. We have used kind of a circuit breaker thinking in our mind when we designed our systems. When a failure happens, a system is able to rapidly adapt itself by isolating failures, converting total failures into partial outages, and automatically recovering from those outages to prevent user impact. As David mentioned, we are stressing our systems out throughout the day using various techniques, be it load testing, be it synthetic traffic, chaos engineering, fault testing, and so on. The reason why we are doing this is because we want to control our destiny. To prevent failures, we practice pessimism with a healthy degree of paranoia. Failures are inevitable and we totally accept that, but we want to fail on our own timeline and ensure that those failures do not impact our users. So what does this mean in real terms? How does practicing failing our worst day look like at Stripe? We do this through a range of simulations and game days. I'll share a couple of examples. Example 1, we will switch off networking to an AZ routinely to see how our systems cope with that failure and how would they recover from that situation. Another example is that we would continuously shift traffic between our regions to exercise our disaster recovery capabilities so that we are not waiting for the worst day to happen. This brings me to the second practice, which is never send a human to do a machine's job. As Balu was saying earlier, that Stripe consistently hits 5.5 nines of availability. And this gives us a very small error budget to work with, which is only 13 seconds in a month. So let's think about this for a second. At best, humans react in minutes, and thus you cannot rely on humans to be able to detect and mitigate incidents within our error budget. Machines, however, react in milliseconds, and only machines would be able to be fast enough to be able to detect and mitigate a failure within our error budget. So what does it take for a machine to react in milliseconds? Well, we have over 1 million CPUs that are dedicated towards observing and monitoring our systems. These systems emit millions of metrics and health stats every day, and we run billions of automated tests in a day. And we combine all of that information in real time and try and detect any anomalies or degradations across our fleet. And if we detect any failures or any degradations, we have automation to be able to mitigate out of that situation very quickly. Let me give you another example of this. So Stripe has its own in-house managed database stack. This database is probably the largest in the world of its kind. It has petabytes of financial data, over 10,000 distinct query types, over 5,000 collections, over 2,000 shards. And you can imagine for a company like Stripe, the database always has to stay up. Failure is not an option. We have to process data, we have to prevent fraud, and we have to make sure that there is no data loss. To maintain a 5.5 nines of uptime, we have designed and built a zero downtime data movement solution from the ground up. This solution allows Stripe to split our shards in real time when there is a traffic surge, and it also allows to bin pack those shards when the traffic is low, all while maintaining durability and health of the underlying instance. In addition, we have invested in a lot of custom observability in our database, such as how frequently are leader elections happening? What's the database watchdog recording? What are the state changes across the database? What's the health of the primary and the secondary node? And again, we use these high fidelity signals in real time to take decisions. For example, if we see that a primary node or a secondary node is not working as expected, they're slowing down, there's a performance impact, we automatically shoot that node down, rebuild the node in the background, and put it back into the quorum. No one notices it. And the best part of all this is that humans are not involved in the critical path. Our database never goes down. Humans build machines that provide defense in depth, and we obsess over improving them. So regardless of a user's integration at Stripe, we monitor their experience as is perceived by them. And rather than singular API response rates, we expand the definition of success to what we call experience quality metrics. We drive a cycle of continuous improvement across all our product surface areas through a 360-degree view of how a user perceives Stripe. So in summary, we assign the responsibility of measurement, detection, and response to robots, while we humans focus on improving the experience for our users. So today we talked about breaking our systems, reacting to failures in seconds. Now let's talk about the most important thing, which is how do we build a reliability mindset? Great ideas are just that. They are great ideas, and it needs an act of will to see them through. Earlier, Balu shared the story of the UK's 911 hotline system that was built in 1937. It took that system 20 years to make its way to the US in the form of our 911 system. And it took yet another 30 years for its widespread adoption across the US. You may wonder, why is that the case? I believe it is due to lack of extreme ownership, which is the third practice that we practice at Stripe. Reliability is not owned by a committee. It comes from the passion and pride that engineers and leaders put into building such systems. And quality requires leadership. Accountability is a term that can be synonymous with placing blame or punishment, but for us at Stripe, it reflects empowering ownership and accountability. At Stripe, employees at all levels are pageable when our users need us the most. Incident remediations are not done in silos or by a central SRE team. It's done by the team that owns and builds that service. So while act of will, discipline, perseverance are words that sound great, how do we institutionalize such things? We do so by continuously measuring and auditing our ownership every day. We run a weekly senior executive review at Stripe where we call on an executive by spinning the wheel. And rather than giving them a prize, we ask them to share their operational learnings for the services that they own and manage. And guess what? Nobody likes this because they have to prepare and present information to a large forum. But we expect each executive at Stripe to be intimately familiar with the services that they own and manage. We expect them to be able to fluently talk about their service and incidents that their service had, root cause analysis, violations of SLOs, SLAs, operational misses, all that, with a view of what are they going to do to improve that service and how are they going to give our users a world-class experience. Leaders are accountable for the end-to-end view of a customer experience versus just their slice. And when we see a continued trend of operational misses, we double down on that accountability. Stripe is not just about sticks though, we embrace carrots as well, and we routinely recognize, reward, and celebrate operational wins every week. This process of accountability has helped us at Stripe to scale reliability as a cultural pillar that has enabled all the leaders to provide end-to-end value for our customers. So, wrapping things up, I'd like you all to leave with 3 key takeaways. Practice your worst day every day. Never send a human to do a machine's job. Remember, designed by humans, protected by machines. And the third one is exercise extreme ownership. And this one goes beyond words. You need to really prioritize for reliability and availability as part of your design. When you're designing your system, these are very important for that. You need to recognize and reward builders and leaders who bring in this reliability mindset and are willing to go the extra mile to help your customers have a great day. But remember, it starts with you. Hold yourself accountable, have a very high bar, have intimate knowledge of your own systems that you manage or work on, and only then can you make others around you accountable. And I know that this is not always comfortable, but this discomfort breeds the right culture. Lastly, it is very important to call out Stripe's exceptional partnership with AWS. This is a foundational part of our ability to drive our reliability and availability goals. We share many similarities with AWS. We are a builder at heart. We are very customer obsessed, and we deeply care about operational excellence at every layer of our stack. We are fortunate to have a strong AWS team who are also our advocates within AWS. We routinely meet and share technical ideas and feedback with critical teams like EBS, EC2, and networking. And I am personally very fortunate to be a part of the AWS Customer Advisory Board, where I can meet and share feedback and ideas directly with the AWS leadership team. We are extremely excited about our partnership with AWS, and we want to win together and build together. And with that, I'll hand it back to Balu.
Thank you, Abhishek and David, for sharing valuable insights and providing expert tips on why and how Stripe build a reliability system. Before we wrap up, I would kindly request a moment of time for you all to complete this survey in your mobile app. And your feedback is invaluable in shaping future re:Invent sessions. If you have any questions, we are available on the hallway. We can answer your questions. With that, I would like to thank you everyone attending this session from all of us over here. Thank you.